In this video, I'm going to demonstrate how we can use the PRoTECT GUI to set up a continuous time stochastic example. So the first thing in the system description is we want to select continuous and stochastic, and you can see we get more options. We then choose the number of dimensions for the system we're considering in dim, and also the maximum degree of the barrier certificate we're trying to find. The Lagrangian degree is optional and defaults to the same value as the dimension. The next thing for us to do is to define the different regions, starting with the state space. We define lower bound and upper bound regions for each dimension, separating them by a comma. We do the same thing for the initial region and also for the avoid region, XU. If we have multiple avoid regions, we can press the button Add Avoid Region to add more. The dynamics are described as a SymPy expression, which uses asterisks for multiplication and double asterisks for exponents or powers. We start by using x1 as our first SymPy variable for the first dimension and x2, etc. onwards. This is very important to get right. The Brownian motion, or the Poisson processes, which are supported by PRoTECT, can be described in the same way as the dynamics, by a SymPy expression. If there is no Brownian motion or no Poisson process, these can be left blank and they will be automatically defaulted to 0. For the Poisson process rates, we once again separate the values by commas for each dimension. You can also include SymPy variables inside of these expressions. In this case, we just choose the value 1/2. For stochastic systems, we offer two types of barriers we can find. One uses optimization, in which case lambda must be set, and the other is without optimizing, in which case the barrier will find its own value of lambda, gamma, and c, which satisfies the condition. The time horizon t is a required parameter because it's included in the confidence that we calculate. You can also set a minimum confidence optionally if you wish, to find a barrier with at least that confidence. The solver is also an optional choice between MOSEC and CVX-opt. If parallelization is checked, then we will take the maximum B degree and we will run all even degrees up to and including this value in parallel. We will store all of these results and then we will return the result with the highest confidence. Note, if optimization is checked, this will nearly always provide a much higher confidence value than when it's not checked. If parallelization isn't being used, then instead we will take the maximum B degree and we will run simply one simulation with that degree value to try and find a solution. When we're happy, we can click the Find Barrier button, and this will try and find a valid barrier certificate. Here you can see the confidence is very low, but if we were to run this again by ticking Optimize with lambda being set to a value, say 10, that this confidence can go much higher. I'm just going to delete the values that we've just got from this run, and I'm going to demonstrate that now for you by checking the Optimize box and then choosing a lambda value of 10. Now when we click Find Barrier, you can see that we found a barrier certificate and that this barrier has a confidence of 0.715, which is significantly higher than the previous barrier. Thanks for watching, and I'll see you in the next video.